In this video, we look at determinants, focusing on what's important for their application in quantum chemistry. The determinant of a matrix is a specific linear combination of products of the elements in a matrix. For a square matrix, A, the determinant is denoted by det A or by vertical bars around A. Determinants are only defined for square matrices. Instead of writing down the general definition of a determinant, let's just look at a few examples. First, here's a 2x2 square matrix. A, B, C, D. The determinant is indicated by vertical bars around the matrix. For this 2x2 matrix, the determinant is equal to the product of the diagonal elements, A times D, minus the product of the antidiagonal elements, B times C. You see, the determinant is a specific linear combination of products of the elements in a matrix. Here, we have two products. We can calculate the determinant for a matrix of numbers. For example, determinant of 6, 2, -5, 4 equals 6 times 4 minus -5 times 2, which gives 34. We can also calculate the determinant for a matrix of other objects, such as functions. For example, determinant of sine of x, cosine theta, x squared, and f of r equals to sine of x times f of r minus cosine theta times x squared. For a 3x3 matrix, the determinant is a little more complicated. Let's start with a general matrix, A, B, C, D, E, F, G, H, I. Determinant. Now, first we pick one element along the top row and multiply it with the determinant of the other two columns in the lower two rows. So we get A times determinant of E, F, H, I. Next, we repeat this by picking the next element in the top row, changing the sign, so negative B, and multiplying it again by the determinant of the remaining rows and columns in the lower two rows. So D, F, G, I. Lastly, we get again flip of sign, top row element C times the determinant of the remaining columns in the two lower rows, which is D, E, G, H. Now we have to work on the 2x2 determinants. Multiplying out, we get AEI minus AFH minus BDI plus BFG plus CDH minus CEG. So we have 6 products total. For higher dimensions, the procedure is analogous. So for a 4x4 matrix, we'll end up with a total of 24 products in the linear combination. What are determinants used for? In mathematics, they're important for the solution of linear systems of equations. In quantum chemistry, we use them for this as well, and also for an entirely different purpose. We use them to generate multi-electron wave functions from one-electron wave functions. The determinant makes sure that the result is antisymmetric and satisfies the Pauli principle. Determinants have a lot of useful properties. For quantum chemistry, the most useful ones are the following. First, if you swap two rows or two columns in a matrix, then the determinant changes sign. For example, in our first numerical example of the matrix 6, 2, -5, 4, if we were exchanging the two columns, we would end up with a value for the determinant of -34. The second important property, even more important in quantum chemistry, is that if two rows or two columns in a matrix are identical, then the value of the determinant is 0. This is a key property. In summary, 3 things are important. First, the determinant of a square matrix is a specific linear combination of elements of that matrix. Second, we have shown a procedure how to evaluate determinants for 2x2 matrices and for 3x3 matrices. And third, in quantum chemistry, the most important property of a determinant is that it is 0 if 2 rows or columns are identical.